Okay, here in lecture B now, we're taking this function, which represents the density of the Earth's atmosphere, h meters above sea level, and we're going to try to use it to figure out the mass of the atmosphere from sea level to 100 meters above the ground around the entire Earth. So you got the Earth here. Drawing it like a circle, but it's really a sphere, right? It's three-dimensional. Actually, it's not a perfect sphere, not just because of the mountains and valleys, but also because the rotation of the Earth tends to sort of flatten it near the poles, so to speak. Though it's probably not noticeable from any pictures. And then you've got the Earth's atmosphere. Maybe I should have made the Earth green and the atmosphere blue, but I made the Earth blue and I'm going to make the atmosphere red. The atmosphere surrounds the Earth. It's like a shell, a spherical shell around the Earth. That spherical shell can be sliced, not with a knife, but in your imagination, into thin, really thin shells. I mean, yeah, this is relatively thin as it stands compared to the radius of the Earth, but we're not going to slice it into thin shells of really small width, delta H width, or maybe delta H is, a millimeter or something. So we're going to be having slices upon slices of shells that together make up the Earth's atmosphere. Why am I slicing it that way? Because this function depends on H. The density is approximately constant at constant heights above the surface of the Earth. I'm sure it's not perfect. There's weather to deal with too, high pressure to low pressure, that kind of thing. It's just an approximation. What is the approximate volume of such a thin slice? So this delta V is going to be the approximate volume. Technically speaking, it is the volume of the outside of the shell minus the volume of the inside, which would involve using the formula of pi r cubed. However, when delta H is really small, that can be well approximated by something simpler. Take the surface area of the shell and multiply it times delta H. Not really justifying that, but I'm saying it is a pretty good approximation, and it gets better and better as delta H goes to 0. Formula for surface area is 4 pi r squared. Surface area of a sphere. The width is delta H. It is an approximation. It's an approximation that gets better and better as delta H goes to 0 and can be justified as the thing we want to use, though we are not doing a justification. What about the approximate mass of that thin shell of width delta H that goes around the Earth? It's a big shell. It goes around the Earth. It's just very thin. What's the approximate mass? Take the density in kilograms per cubic meter times the volume, which would be in cubic meters. Delta of H times delta V. Delta of H, this is an approximation as well, times 4 pi r squared times delta H. But since I'm going to have a delta H in there, really I'd want to get r in terms of H, wouldn't I? R is the radius, the distance between the thin shell and the center of the Earth. Really, I need an expression for r as a function of H. Now the book gives you the information that the radius of the whole Earth is about 6,400 kilometers. That is 6.4 million meters. Those are commas, they're not decimals. Then I go h meters above the surface of the Earth. R really, as a function of h, is 6.4 million plus h. The total mass, then, is going to be approximately the sum of things like this. whole expression and put it down there. And then you say, hey, that expression looks like a Riemann sum for that function right there, delta of h times 4 pi times 6.4 million plus h quantity squared, and therefore that's the function to get the best approximation. And it really is an approximation, because this is an approximation. The integral itself is even an approximation. Would that be a very easy integral to do by hand? No, I would not want to do it. So we are going to make sure we're zoomed in with the camera there on Mathematica here. We're going to have Mathematica do the integral for us. If you had to do it by hand, if your life depended on it, could you do it? Yes, though it would be hard to do it without making a mistake. You could use integration by parts to help you do it. You probably want to break it into 3 integrals or something. Integral from 0 to 100, because we're talking about the first 100 meters of atmosphere. The function is 4 pi times delta of h, which is 1.28 times e to the negative 0.000124 h. Then don't forget your 6.4 million plus h quantity squared dh. This is going to be based on this model for the density, which evidently some scientists figured out as a good model. Going to give us an approximation for the mass of the Earth's atmosphere from 0 to 100 meters high around the whole Earth. About 6.55 times 10 to the 16th kilograms. What is that? 10 to the 6th is a million, 10 to the 9th is a billion, 10 to the 12th is a trillion, 10 to the 15th is a quadrillion. Got about 65 quadrillion kilograms here. Plenty massive. Okay, and that's the atmosphere. All right. Any questions about that? All right. That's the physics for today. Now we're on to finance. Present and future values. First today, we're doing them for discrete payments. Last Friday, we talked about present and future value for one individual payment. What do I mean by payment? Well, payment just means money that's being transferred. You could be making a payment for something, either now or in the future. You could be the one being paid, either for a service or a product you sell to somebody, or you could even be paying yourself, like putting money in your bank account, right? That could be thought of as paying yourself. Or it can be thought of as paying your bank, actually, because you are giving them your money for a time being. Do you know they use your money? They don't keep it locked away in some vault. I mean, maybe part of it, but they use your money to loan to other people under the assumption that not everybody's going to come want to get their withdrawal at once, right? Like in It's a Wonderful Life, George Bailey had to explain to the people, no, you can't all withdraw your money all at once. You don't want runs on the bank, because the bank doesn't have everybody's money at once. It can give individual people their money at once on the assumption that not everybody comes. Maybe only 5% of the people withdraw money on a given day or whatever. The basic formulas that we wrote down look like this. B equals P times 1 plus R to the T, which was equivalent to P equaling B times 1 plus R to the negative T. That is the situation where R is thought of as an annual compounding rate. Now, if it really is a bank, money in a bank, they really do give you your money at only certain times. Maybe once a year or maybe once a quarter, more likely. But for us, technically speaking, it will be okay for us to use these formulas for values of t that are not whole numbers. Like we can plug in t equals 2.743 if we feel like it. And get these amounts. B is sometimes thought of as representing balance, but it represents future value for us. P sometimes represents principal, what you deposit, but it's going to represent present value for us. And we can use these formulas irrespective of whether we're thinking about bank accounts or not. Just purely based on this idea of the time value of money. That $100 today is worth more than $100 tomorrow, or $100 a year from now, or $100 10 years from now. It's worth more right now for three main reasons. I only mentioned two last time. One main reason is just psychological or practical. I want my money right now. I don't want to wait. Another reason is because if you got the money right now, you could invest it and get more in the future. So if you're going to trade $100 right now for something in the future, you better give me more in the future as an equivalent amount. And the third reason that I had mentioned was inflation. Generally speaking, your buying power goes down over time, which means prices are going up, is the way we observe it. Generally speaking, not always. Those three reasons are reasons why you might say there is a time value of money, and you can think about that idea irrespective of bank accounts. Okay, though it is often thought of in terms of bank accounts or investing. There's also continuous compounding. Where the R represents an interest rate chosen in such a way that you are getting money continuously, so to speak. Your money is growing continuously, but actually, again, in both these equations, you can think of your money growing continuously, even in both situations. It's just a different way of representing the interest rate is really the main thing in these formulas. The first way is the way we're going to think about this stuff initially. The second way is the way we will end up thinking about the stuff in this class, at least in Chapter 8. Chapter 9, we might go back to this because the second way is going to be easier to deal with in terms of differentiating and integrating. Right? It's easier to integrate things like this than it is to integrate things like that. It's not super hard to integrate things like this, but it's messier. You get natural logs involved. I don't know if you remember that or not from Calc 1 when you try to integrate things like this. By the way, these two things are not equal. If R in both is the same thing, they're not equal, which would make sense why we'd have different formulas if they were equal. Two different values of R could make them equal. Two different but related values of R could make them equal. But for the same value of R, they are different. Okay. All right, let's do an example where we use these formulas for figuring out the present value and future value of something called an annuity. What's an annuity? Annuities in general are just payments made over time. And the simplest kind of annuity is where you make the same payment in equal increments of time over a certain finite amount of time. So I'm going to draw a number line. Mark off whole number values on the number line from 0 to, let's say, 10. And if you like, you can imagine you won the lottery. Okay, if you like. I don't gamble personally. I think it's a bad idea, and so I don't gamble. And not being a good steward of my money. But if you do gamble, you could win the lottery, and you could win your winnings in discrete payments, not all at once necessarily, over time. Maybe they give you $100,000 starting right now at time 0. And then every year after that for 10 payments. So $100,000 right now, $100,000 1 year from now, $100,000 2 years from now, $100,000 3 years from now, etc. If they give you 10 payments, At time 8, that's your 9th payment actually, and your 10th payment is at time 9. What I'd like to do is find two things. I'd like to find the present value of this annuity. What is it worth, so to speak, at time 0, based on a certain interest rate. And the future value at time 10. That's why I bothered to put the 10 in there. There's 10 payments total, the first being at time 0. The 10th would be at time 9. What's the present value right now, and what's the future value at time 10? Those are the two things I want to find. The present value of the annuity. Let's go ahead and assume it's based on the annual compounding formula. And let's pretend it's a great bank account. 8% interest rate. Wow. Actually, I'm choosing that because that actually was my savings account's interest rate back in the early 1980s when I was a little younger than you. I'm not lying. 8% was my savings account interest rate. I was earning $8 for every $100 every year, which is crazy because today it's like 2 cents for every $100. How could they give me such an interest rate? It's because they had to, because inflation was so bad that they had to give people a huge interest rate, huge rates of return to entice them to actually save. Inflation was so bad that they had to do that. But inflation has not really been much of a problem in recent years. What you do is you find the present value of each of these payments and you add them up. The present value of the first payment, which is right now, is that amount, $100,000. You don't have to do anything to that because it's at time 0. What's the present value of the second payment at time 1 of this $100,000? You have to pull it back in time, so to speak, by 1 year. It's 1 year in the future. Use this equation with t equal to 1. So you get a negative 1 power. Take the $100,000, pull it back in time, so to speak, 1 year. Multiply this by 1 plus r, which is 1.08, to the negative 1 power, because it's 1 year back in time. Are you doing the camera here? Good. The next payment of $100,000 is 2 years in the future. What's its present value? You've got to pull that back in time 2 years. That gets done by multiplying by 1.08 to the negative 2 power. The fourth payment at time 3 gets pulled back 3 years. 1.08 to the negative 3 power, etc. The last payment of $100,000 is at time 9, so that's got to get pulled back in time by 9 years, multiplied by 1.08 to the negative 9 power. Ugh, I don't really feel like doing that on my calculator. Can it be done without too much pain on Mathematica? Yeah, it can be. So now let's focus on the Mathematica here. On the Basic Math Assistant, there is a summation button right here. Can you see it down there? Click on that. We've done that before. I want to represent that summation in summation form. Each term has a 100,000 in it. And there are 10 terms. They all involve 1.08 to some negative power, including the first one, because you could think of that as 1.08 to the 0 power, or negative 0 power. So actually, maybe it's better to start I at 0 instead of 1. Go to 9. I mean, you can do it either way, but it might be simplest to do it this way. That's a summation that should give us the answer. Let's see if it does. That's what it tells us. Oops, nope, sorry, mistake. Negative I power. There we go. 724,689. Now I should have tried to guess the answer without typing that. The answer did have to be less than $1 million. I mean, our total amount of money that we get is $1 million, but those amounts are in future values, which in present values is less. $100,000 in the future is worth less now, because you can invest less now to get to that amount later. So I knew it had to be less than $1 million, and it is. Hard to say how much less than $1 million, but I will tell you before our break here that if the interest rate had been higher, or actually lower, let's go with 2%, the present value is actually bigger when the interest rate is low. Why? Well, let's see if it is bigger here. Yeah, it's a bigger present value. Why? Because if the interest rate is lower, you've got to invest more money now to get the same thing later. That's why the present value has to be higher. You have to invest more now to get the same thing later, to get the equivalent amount, if the interest rate is lower. All right, let's take a 3-minute break.